Hi, Kinesiology 3010. This is our last lecture on descriptive statistics. We're going to go into a little bit of review and look at standard scores and how we compare scores using some of this descriptive information that we've learned so far. Okay, standard scores are scores that have been broken down and standardized based on the mean of that group and the standard deviation of that group. So we've broken down our scores and put them in terms of the mean and standard deviation. Rather than using the individual measurement from that score, we're able to compare these scores a little bit better when we have a viewpoint of how they all spread out compared to the mean. We'll get more into this in a little bit. Okay, so this is even more practical when it comes to comparing multiple different tests. So in this case, we have a basketball coach who wants to evaluate his players in a more comprehensive perspective, so not just one skill at a time. So he wants to know how they're doing in levels of skill, fitness, and basketball tactics. So we would use 3 different tests to measure each of these different qualities of basketball performance. Okay, so they have 3 different tests, or they have multiple different tests. Say a free throw test for free throw skill, basketball dribbling skill, 35-meter sprint for a fitness, sit-up for a fitness, and a tactical knowledge test. So we have 5 total tests over those 3 domains of fitness, tactics, and skill. But how do we compare these? Okay, how do we look at these from a similar perspective? Can I compare 36 sit-ups to 6.03 second 35-meter sprint? No, they're in different units. Okay, sit-ups is in number of units. 6.03 is in seconds. Basketball dribbling, this is in seconds, so I can compare the 2, but those are different tests. Okay, one's dribbling, one's not dribbling. That's a huge factor when it comes to comparing those 2. And can I compare 6 out of 10 free throws to 60 points out of 100 on their tactics test? So it's when we have different units, we have different tests, we need to find a way to compare them all to see, is this good? Is this good? We need to have that evaluation portion. Is 6.03 seconds in a 35-meter sprint good? Is it bad? Is it above average, below average? This is where our standard scores really come in. Okay, so here's another example, give you another view. Okay, so say we have a student, Dave, gets a 50 points out of 60 on statistics midterm exam, and he gets a 50 out of 60 on his calculus midterm. Did he do the same? How did he compare those 2 exams? Did he do better on his statistics class, or did he do better in his calculus class? Okay, how do we compare those scores? Okay, we could say that 50 out of 60 was the same as 50 out of 60 on the calculus midterm, but if his statistics class was a 1,000 level course compared to his calculus class, which was a 4,000 level course, were those the same when it comes to knowledge base, when it comes to difficulty, when it comes to assessing knowledge within that field? So we can't really compare them unless we use another form of measurement or break down those measurements. How we do this is by using standard scores. Okay, so we take the standard score based on that test, so the mean of that test. So we have a group of individuals that take that test. We find the mean. So what is average for that exam or average for that test that we're giving? We also want to know the variability of the scores. Okay, so how those scores are spread out in comparison to the mean. And then we want to know how far Dave scores from the mean, okay, based on that variability. So how far is Dave's score away from the mean? So is he average? Is he above average? Is he very above average? Is he very below average? Based on what is the variability for those scores? Okay, what is normal difference between scores? If you remember from our previous lecture, variability is how those scores are spread out in comparison to the mean, and we can view them in terms of standard deviation, or the square root of the variance. Okay, that standard deviation gives us units across our distribution. So if you remember from our previous lecture, that 68% of scores are within one standard deviation, positive or negative, or forward, above, or below the mean. So this gives us a viewpoint of where Dave's score is, or where one individual score is, in comparison to what is normal for that group, or what happens very frequently, or where that kind of central tendency is. So if we know that Dave's score is 2 standard deviations above the mean, we know that he is extremely above average, and he is likely performing closer to 95+% better, or much better. So in this case would be towards that top level of performance for that group. If we see that Dave's score is -1 standard deviations, or 1 standard deviation below the mean, we know that he's scoring about 34% lower, or kind of lower than that average. Okay, so this gives us a viewpoint of where these scores, where individual scores are in comparison to the entire group and to the average of that group. Okay. We create these standard scores. We use 2 different types. We use Z-scores and T-scores. We'll start out with Z-scores. Okay, Z-scores give us the exact location on that normal distribution where every individual score is in terms of the standard deviation. So Z-score units are standard deviations for that individual test, for that individual group. The raw score is the individual score that was actually measured, or the observed case. So we convert our raw scores into Z-scores for that group that we assess. So a Z-score always has a value of 0, and standard deviations are in terms of 1. Okay, so if this doesn't make sense, we'll see it in another view right here. So 0, a Z-score of 0 is equal to the mean. A Z-score of 0 is equal to the mean. A Z-score of 1 is equal to 1 standard deviation greater than the mean, or the mean plus 1 standard deviation. A -2, a Z-score of -2 is equal to 2 standard deviations below the mean, or the mean minus 2 standard deviations. And those standard deviations and those means change based on the population and based on the test. So they're very specific to the test, but it also puts us in terms of where they are in comparison to the entire group for that score. Okay. Z-scores have decimals and can be negative values. Okay, so we can be in between 0 and 1. So you could have a Z-score for your individual test of positive 0.23, or you would be 0.23 standard deviations greater than the mean. It can also be negative, like -2 or -2.1, which would be 2.1 standard deviations below the mean, or below the average. Okay, so these Z-scores represent a point on the normal distribution curve. So where we stand in comparison to the mean in terms, or in units of, standard deviation. So why would we even use this? So why is this important? Okay, it tells us where these raw scores are located. So it tells us where each individual participant scored in terms of the entire group. Okay, and then if we also use different tests, so say our basketball example where we have 5 different tests, if we convert all of the participant scores into Z-scores, we can compare them all in terms of Z-scores, because if I have a Z-score of 1 in one test, but I have a Z-score of -1 in the next test, I can say that I'm above average in one and below average in the other. So I can compare where individuals are in comparison to what's average for that group based on those tests that that group has been given. So we'll go further into that. We also use these in kinesiology. So if any of you are, or for all of you are kinesiology majors likely, we use Z-scores when it comes to measuring bone mineral density. So we measure bone mineral density through the DEXA scan. It's a full body X-ray exam that determines the bone mineral density of the individual, or how much calcium we have stored within those bones. Stronger bones have more density. Weaker bones have lower density. So if we measure your bone mineral density and you are in the positive, or you score a Z-score of the positive compared to everyone else in the world who's ever taken that DEXA exam, so it's comparing it to the average, or what is average for bone mineral density. If you're above, you're good. You have high quality dense bones. You're probably physically active. You probably have a nutritious diet. You probably do some kind of training of some sort. But if you have a Z-score of less than -1, okay, between -1 and -2.5, so in this zone, so you are 1 standard deviation to 2.5 standard deviations below the mean, that is termed as osteopenia. And less than -2.5 is considered osteoporosis. So this is a loss of bone mineral density, putting you at an increased risk of fracture. We see this a lot in older adults, especially older females. If you have osteopenia or osteoporosis, you are at a very high risk for developing a fracture if you fall, even from very low heights, because the bones have become so brittle. So you'll see this if you going further in kinesiology, you'll see these terms used further. So it's not just learning statistics for statistics' sake. Okay, so how do we find these Z-scores? Okay, pretty simple formula. You probably recognize this formula a little bit from your first lab where I gave you an example of raw score and Z-score. Okay, the Z-score is taken from that score subtracted from the mean divided by the standard deviation. So you do have to calculate the mean. You do have to calculate the standard deviation before you can do this. Because we are taking that score, subtracting the mean from that score, and dividing it by the standard deviation. So we're converting that raw scores units to Z-score units. Okay, so here's an example. So I have a high school student and they're doing a fitness test. He does 45 laps for his pacer test and 20 for his push-up test. Okay, how did he do in comparison to the group? Okay, this doesn't give me that much information, but when we look here, we can see that the mean for the pacer is 50 and the standard deviation is 4. The mean for the push-up is 18. The standard deviation is 3. So I can convert this student's scores into Z-scores. So use my Z-score equation, take my means. I have my raw score, take my raw score minus the mean, divided by the standard deviation. Okay, I'll take my raw score for my push-ups, subtract the mean, divide by the standard deviation to get my Z-scores for the 2 tests. So how my student did in comparison to the entire group. Okay, so how would you interpret this? Okay, what do those negative and positive mean? Okay, negative doesn't mean less, positive doesn't mean more. So the negative and positive tells us which side of the mean that Z-score is. Okay, so negative means below the mean, positive means above the mean. The actual value of the Z-score, so the numerical value, tells us how far in units of standard deviation that raw score is away from the mean. Okay, so a Z-score of -1.25 is left of the mean by 1.25 standard deviations, or right around here. A Z-score of positive is above the mean or greater than the mean and this is both 0.27, a z-score of 0.27 above the mean would be right here. So now I can see that my students' scores were better than average in push-ups, but very below average when it came to pacer. Okay, so maybe they have lower cardiovascular fitness, better muscular endurance. Okay, so this gives me some more information, but this is norm referenced. Remember, this is a norm referenced situation, so we're comparing it to the mean of the group. If you have a group that is all very low fitness, it may skew your interpretation, but it gives us some more information. Okay, so here's my z-score. This indicates that my raw score is located 1.25 standard deviations below the mean, so below average. Okay, 20 push-ups compared to 18 is 0.67 standard deviations above the mean. Okay, so it's above the mean. Okay, so this tells me how much or how far I am away from that midline. Okay, if we know the z-score, if we know the mean and the standard deviation, we can also break it back down to find what the raw score was. Okay, so if I have, here's my equation here, and my raw score equals the mean plus the z-score times the standard deviation. Okay, so if the mean is 60, standard deviation is 12, and the z-score is 0.25, and I want to know what was that participant's raw score. Okay, what did they actually score on that test? Okay, I can plug those in, and I find, in this case, my raw score was 63. Okay, because it's 60 plus the standard deviation times the z-score. Okay, so we're converting that away or out of standard deviation units back into whatever units we tested using. Okay, so the mean is 60 and our standard deviation is 12 and our z-score is negative 1.25. Plug that in. You can do that on your own. We see the x is 45. So this gives us some nice, easy information. This tells us where we are in comparison to the average, compared to the mean in terms of standard deviations or the variability. And we can also convert it back if we want to go back to find out what was that participant's actual raw score. Okay. We also have t-scores. T-scores represent the z-score, but they're a little bit easier to view when it comes to presenting information. Okay, a t-score has a mean of 50 and a standard deviation of 10. So these put us on a 100-point scale rather than looking at positives and negatives, rather than looking at decimal points, specifically like small decimal points like 1.03. This just gives us an easier view and goes off kind of looks similar to our percentile chart. So t-scores are always positive, and we're going 0 to 100 on that scale, with 50 being the mean and 10 being each unit of standard deviation. So we can convert, or we can calculate our t-score by using the equation 50 plus 10 times the raw score minus the mean divided by the standard deviation. Or if we already know the z-score, we can use 10 times the z-score plus 50. Okay, so we're just broadening that scale out so that we can use rather than a -5 to +5 scale, we're going from a 0 to a 100 scale. This often is easier to present because you can say that 50 is right in the middle, and how are they spread compared to 50 rather than seeing positives and negatives. Sometimes that can be confusing when you're presenting information to other people. Okay, so here's our example here. I recommend trying to pause and do this on your own, calculate the z-score, calculate the t-score. But I'll go through these also. So if you want to pause and practice, go right now, calculate the z-score and calculate the t-score for these two situations. All right, now I'll go through how to do it on, if you don't know, or you can check your answers. Okay, so to calculate our t-score, it would take 50 plus x times the raw score minus the mean divided by 5. And then in this case, we'll take 50 plus 10 times 8 which is our raw score, minus 25, which is our mean, divided by 10. Okay, so in this case, I have a t-score of 20. In this case, I have a t-score of 33. Okay, you can backtrack and calculate the z-score also. I'll just keep it for t for the case of this example. Okay, now what does this mean? What does this tell us? Okay, let's do a little quick interpretation. If we know that 50 is our mean, 20 is 30 points below 50, and that means it's 3 standard deviations below. Okay, so this is, if we have a number, a t-score below 50, we know we're under the mean. T-score greater than 50, we know we are above the mean. So in this case, both of these participants, these raw scores, scored below the mean, or multiple standard deviations below the mean. Okay. So now I'm posing some questions for you. Can z-scores from different tests be added to make a total z-score? Yes. Okay, can you combine z-scores with a 1-mile run test and a sit-up test to find overall fitness z-score? Absolutely. This is one of the great points about these standard scores and why they become standard scores, is because we can compare them across groups or across tests within the same group. Okay, that's the key. It has to be within the same group. Okay, so we know how to convert raw scores into standard scores, so either z-scores or t-scores. And then this allows us to combine and compare information for different measurement units. So we can compare sprints to free throws to basketball dribbling. Even though they're different tests within that group, we can compare each individual compared to the average in terms of standard deviation and find a total score for that individual, so we can see how they did in total compared to the rest of the group. Maybe if you're trying to see who's making varsity, JV, and freshman teams for your sport. So here's an example. Okay, what is the student's total score on the fitness assessment? Okay, remember back from our earlier assessments with the pacer and the push-ups. If we add those z-scores together, okay, this gives us a total score of negative 0.58. So this student scored in total, using all of the tests, about 0.58 standard deviations below the mean. So this individual was below average when it came to total fitness compared to the group. Okay. What are some possible limitations to this? Okay, we are comparing to an individual group. Okay, you can't compare group A compared to group B if all the participants are different, because that average and those standard deviations have changed because you're using a different population. So that's one of the limitations. And also we have with this, if you have a group that is extremely poor on average compared to other groups, so if Group A is much lower fitness than Group B, an individual's z-score of, if someone scored average in Group A and it's a lower fitness group compared to someone who scored average in Group B, that's a higher fitness group. So those raw scores are very different. Okay, those two, you may say they both have the same standard score, but Group B, the raw score is much higher. They have a much higher fitness. So that's one of the limitations, because it is a norm reference system, or reference to the population that you're dealing with. It does depend on the population's level within that test. So low level or high level, it's going to skew your z-scores if you have one individual who is very above average compared to that group. So making sure that we have accurate samples will help to limit some of that. Okay, so here's some examples of how we also use these. So things like SAT and GRE scores, we'll often use the same z-score scale. So we can have our 0 and what is above the mean and below the mean. If you're looking at IQ scores, Okay, the mean is around 100. Okay, 115 would be 1 standard deviation above, 85 1 standard deviation below in these cases. As you can see, 1 standard deviation in this case is 15 IQ units. If we subtract 15, we get 85. So the units in terms of mean and standard deviation, we can calculate that. Whatever 1 standard deviation is, subtract the mean, you have your standard deviation value, if that's another question for you. Okay, so now I have some practice for you. This practice should be included on the back of your week 3 lab. So at the end of your week 3 lab, you need to have descriptive statistics practice, okay, so that you can go through there. So this practice, okay, is to create a frequency table and calculate these 10 variables. Okay, these 10 variables. Okay, we need n, which is our sample size, how many scores, okay, how many observed cases, the mode, the most frequently occurring score, the median, okay, score or scores, the median, which is the 50th percentile, the right smack dab in the middle value, the mean or the average, the range, so the highest score minus the lowest score, the sum of the scores, okay, so that means adding all the scores up together, the sum of squares, which means squaring each individual value and adding those squared values together, the squared sum of values, okay, so that means taking all the values summed, so are your answer for number 6, and squaring it, so summing all the values and that quantity is squared. Calculate the variance, okay, these previous ones, so the sum of squares and squared sum of values should help you calculate the variance, because those are required. Also your n is required for your variance, and remember standard deviation is the square root of the variance. Okay, so pause this right now, write down all of these individual scores. I recommend you create them into a table, okay, with those scores going down in a column, and then creating the sum of squares and squaring the values, putting them next to it. It will make it easier for you to calculate those and visualize them. Okay, so pause the video, write down all of these scores, and calculate these 10 pieces of information. Okay. Also, I have just for your reference here, the variance and the standard deviation. These are our equations, so if you forgot them, if you don't have them written down in your notes yet, variance equals the sum of squared values minus the sum of the values quantity squared divided by the sample size all over the sample size minus 1. And then our standard deviation is the square root of the variance. So you have to calculate the variance to find the standard deviation. Okay. Additionally, with that practice, okay, from previous data, calculate the z-score from the following values. Okay, so from those values, from these 4 values, 2, 8, 3, and 10, based on the data set that you just wrote down, calculate the z and the t-scores for these 4 variables. Here, these 4 individual scores, z-scores and t-scores. Okay, so you should have 10 pieces of information, and then you should have 8 more answers also. Okay, so 18 individual answers should be included as your standard score and your descriptive statistics practice. Okay, your descriptive statistics practice that you're going to include on the back of your lab. Okay. I'll also include the answers in our week 4 lecture. So you don't get the answers yet. I will include them in our week 4 lecture so you can view them and you can check your answers there. But you do need to go through this practice it is going to help you when it comes to our quizzes and our exams, and understanding how to mathematically compute this information. That's about it for this lecture. Hopefully everything is going well. Please email me if you have any questions. Please stop by my office hours if you're having trouble. If you're having trouble with the mathematics, please let me know. I'm happy to help. Thank you very much, and enjoy the rest of your day.